Hello, everybody. Okay, so today we're going to do some pH calculations, and in order to do that, I'm going to ask you to download or install the Desmos app in your phone. If you don't have it already, just go ahead and hit pause, go to the App Store or whatever, and find the Desmos app, Desmos, and download that. I don't know if there's like a graphing calculator one and a scientific calculator one or not. You just need the scientific calculator one if there are two different options. So once you do that, you'll be able to go ahead and do this. So it is Thursday, May 21st, and we're going to learn how to do some pH calculations. So pH is something that was invented by humans. pH isn't something that exists in nature. So the deal is that here it is right here. You guys know that the pH scale goes from 0 to 14. What you didn't know is that it actually goes less than 0. You can have a negative pH, and it actually goes greater than 14. You could have a pH of 15. So the way it works is that acidity, as we learned earlier, is a measure of the hydronium ion concentration of a solution. That's the concentration of hydronium ions. Hydronium is oftentimes just shorthanded to an H plus or proton concentration, but we learned that that's not really what's going on because you don't have free floating protons. They're super reactive with water molecules to form hydronium. So here, let's check this out. Here. Boom. Okay, so I just took this one. You guys can copy this in your notes. If you take the pH scale, and I have it going all the way from -1 to 15 to show that it does not, in fact, just start at 0 and stop at 14. It can go less than 0 and it can go more than 14. How much more? A little bit more. So each one of these pHs, pH 0, pH 3, pH 7, pH 10, and pH 13, and of course we're getting more basic this direction and we're getting more acidic this direction. But each one of these pHs corresponds to an actual concentration of hydronium. So this is the nature part right here. If you have a hydronium ion concentration, that's a concentration, that's what the square brackets mean, of hydronium of 10 to the 0 power, which is 1. So this is 1 molar right here. If you have a hydronium ion concentration of 1 molar, that corresponds to a pH of 0. If it's 1/10 molar, that's a concentration of 1. If it's 1/1000th molar, that's 10 to the -3 molar. Do you guys believe me that this is the same thing as this? Well, if you don't, I don't know what to tell you. Because it is. So anyway, 1/1000th molar, that's 0.001 molar. All these are the same thing right here. That would have a concentration of 3. So all you have to do is count 1, 2, 3, pH of 3. Isn't that nice? So 10 to the -7th molar would be a pH of 7, and that's neutral. That's pure water, has a concentration of 1/10 millionth molar. Yes, hydronium. 10 to the -10th would be 10, pH of 10, and so forth. Sound good? So how do we get from this number to this number? This is the part where humans came in. So if you got your calculator here and you can open up Desmos like this, I'm going to zoom in on this sucker so you can see these botones. Yeah. Okay, so there's 3 menus in here. There's the main menu where we are right there. There's keyboard right there. And then there's functions right here. So what we want to do is figure out how they're getting from this number to a pH of 3. And here's how. It turns out that pH is equal to the opposite of the log of the hydronium ion concentration. And humans invented this. There's such a wide range of acidity, they needed to put it on the log scale in order to condense it into something more convenient. Otherwise, you wouldn't end up with a scale of 1 to 15. You'd end up with a scale of 1 to 10 to the 15th, whatever that is. So it'd be cumbersome. So instead, they broke it down by the powers of 10. And that's where this comes. And to tell you the truth, I don't understand how it works too well, but guess what? I'm a biochemist, and that's how we roll. We don't even care. All we care is that it works or if it doesn't work. And if it works, then that's enough for us. And you guys are biochemists too. So you don't care either. So here's how it works. If you want to find the pH, you need to know the concentration of hydronium. So if the concentration, let me get rid of this so that it's not confusing us there. So if you know the concentration of hydronium, well, like in this case right here, 10 to the negative 3 molar, then here's what you do. Go to main right here, and we want to find the log of 10 to the negative 3. So here's what we're going to do. We're actually going to go to function, and we're going to hit the log button right. Oh, sorry. I'm going to start over. Clear all. So we're going to go to the function area right here. So it starts with the main, but we don't want to be there. We want to be with the function right here. So we want the log, and it puts in some parentheses right there for us, which is nice. So we want the log of 10 to the negative third power. To get to the negative third power, I'm going to push this button right here. Dink. So that puts it up in the exponent position, 10 to the, and I'm just going to hit the minus sign, 3. And it shows up with the answer as negative 3 because I messed up actually. This is not a pH of negative 3. What I did is I forgot about this right here. It's the opposite of the log of the hydronium ion concentration. So let's go ahead and go back and do that over again. Clear all. We want the opposite. So I'm going to hit the negative button right here. The opposite, and then I'm going to go to function, log, and then I'm going to go back to the numbers of 10, and then this exponent button right here, to the, and then negative 3. And then it says that the pH is 3. And we already know that if you have a hydronium ion concentration of 10 to the negative 3, that your pH is 3. We already know this. That's nice. So now you know why it's 3. But, oh yeah, by the way, the answer here is 3. Yeah? 10 to the negative third. But what do you do when it's not like a whole number? Like we don't even need this dumb equation right here. We can just look and be like, okay, 10 to the negative 3 is 3, 10 to the negative 7 is 7. But what if it's not a nice even number like that? Then that's why you're going to have to use this formula right here. So what if the hydronium ion concentration is not a whole number? What do you do then? Well, here's what you do. So let's say, for example, we had a bottle of hydrochloric acid, and it says that it's 1/4 molar, 0.25 molar hydrochloric acid, and it was bottled by Gady on 5/21/20. Yeah? So how do you figure out the pH of this solution right here? Well, all you have to do is remember that hydrochloric acid is a strong acid. Therefore, it fully dissociates. Go back to that video on that if you don't believe me. I don't think I have it right here handy, but Go back to that video if you don't believe me. HCl, every single one of these hydrogen ions is going to react with a water molecule and break apart. So whatever your concentration of hydrochloric acid is, that's also your concentration of hydronium. So hydrochloric acid is a strong acid. Therefore, it fully dissociates. Therefore, 0.25 molar hydrochloric acid is 0.25 molar hydronium. Yeah, that's right. So what we need to do is we need to take the opposite of the log of 0.25. 0.25 because that's the concentration of hydronium, because pH is the opposite of the log of the hydronium ion concentration. So for a strong acid, the concentration of the acid is the concentration of hydronium. So the concentration of hydronium is 0.25. So I need to get out my calculator here and hit clear all. Let me zoom back in here. And we're going to want to do the opposite of the log of 0.25, just like that. And it shows us that the pH is 0.6 about. So the pH of this solution is 0.6. Yeah, that's great. So another way, like, you know how I didn't use the exponents right here? Another way that you could think about it is that 0.25, if you take that decimal and you put it into the between the ones place and the tenths place, then that's 2.5. But the real number is smaller than 2.5. How much smaller? 1 order of magnitude smaller. So we're going to say times 10 to the negative 1. You could put this into the calculator also for the hydronium ion concentration right here, and you'd get the same answer right here. Whoa. Right here, you get the same answer. What do you guys think about that? I think I might have messed that up a little bit. You could take this 2.5 times 10 to the negative 1, because that's also the hydronium ion concentration. Plug it in there, and you're also going to get 0.6. So I'm going to give you guys some practice problems with that. Just remember that if we're talking about a strong acid, then we're talking about, and you know the concentration of the strong acid, then you also know the concentration of hydronium, because they're the same thing. The concentration of a strong acid solution is equal to the hydronium ion concentration of the solution, and vice versa. So remember that when you're doing those practice problem, friends. Okay, bye.